in southern France, and both Maurizio and Ba-Hien have been doing a lot of amazing work in Bayesian deep learning. As you probably know, which is about uncertainty quantification in deep neural networks. And yeah, very much look forward to their exciting talk. They're going to give it together. And yeah, without further ado, let's take it away, Maurizio.
Well, thanks a lot. Thanks, Stefan, for the nice introduction. It's and thanks everyone for being here today. It's a great pleasure to be here and in this very great place to do machine learning. And today we're gonna talk about ways in which we can specify good priors for Bayesian deep learning. So the idea really is that I will just introduce briefly what we mean by Bayesian deep learning. Give a bit of maybe historical context as well, and our experience and how what we found challenging in working with these kind of models, and later Ba-Hien is going to talk about ways in which we can actually specify good priors for these models, which we think was the problem associated with making these models actually work. And then, so we're gonna first talk about the supervised learning problems in the first part, and then we're gonna move on to unsupervised learning by looking at Bayesian autoencoders. So in the literature, you may have heard about variational autoencoders, which are generative models, and you can do representation learning, and they're really great. But the problem is that you're tying yourself to use variational inference. And now, by looking at this new way that we have to do good priors for Bayesian neural networks, we thought, okay, maybe we can take a Bayesian neural network in the configuration of an autoencoder. It's not a generative model, but we can make it generative by quite easily. But now we're not tied to variational inference anymore, and we can use other ways of doing inference. For example, Markov chain Monte Carlo, which we use throughout this work. And actually, we can use this in an effective way, as we're going to see, for generating nice faces and nice images and so on. And then we conclude. So as you may know, deep neural networks have been very popular in the last couple of decades now. I would say they've ramped up the performance on lots of they broke records on very many applied problems. But unfortunately, as you may also know, we don't get uncertain quantification out of deep neural networks unless we do something extra. And so if we just take a neural network and we have some weights and biases, and we typically optimize some sort of loss, and we're going to obtain some sort of point estimate for the parameters. Obviously, I mean, there are different ways in which we should maybe regularize these models by L2 regularization, early stopping, or dropout. And so these provide good ways to do regularization to avoid overfitting. Or some recent work also says maybe you should train them to overfit massively, and this also generalizes well for some mysterious reason. Mysterious to me, at least. I have to study that literature more. And so the idea is, in order to obtain quantification uncertainty for people like me, coming from a background in Bayesian statistics, is to say, well, let's just say we put a prior on these parameters and we try to do Bayesian inference over the parameters and biases of these models. And so typically the posteriors are going to be, for these models, we have some sort of likelihood, which measures the likelihood of the data given the parameters, which you can think of some sort of exponential of some negative loss, if you like. So likelihood and loss are, good loss means good likelihood, okay? And also we can put a prior on these parameters. And now if you multiply the likelihood and the prior, we get a posterior. But the difficulty in working with this treatment is that this posterior is difficult to normalize, because it's, requires this P of W given data to be a proper density over W. So if you have a large dimensional problem with a lot of parameters, this would mean, solving intractable integrals to be able to normalize properly this density. And so this is the difficulty. And then if we can access this posterior or somehow sample from it, then we can try to obtain this posterior predicted distribution, which integrates out the parameters in predictions. All right. So this is a simple expectation of the predictive under the model. Okay. So I just wanted to give a brief deep learning timeline. I quote Mackay in 1992 as one of the first references talking about Bayesian neural networks, but I'm sure, you know, someone may find one day that there is something earlier about Bayesian neural networks. And there's been also some significant understanding of the connections with the other models in machine learning, which are Gaussian processes, which we're going to also discuss in this presentation, by Rutherford Neal in 1996. So if you take a shallow neural network and you take the number of neurons to infinity, you can draw some connections with Gaussian processes. And so naturally, also, you can now start thinking about deep Gaussian processes as ways to, as some sort of probabilistic version of neural networks. And like some interesting developments that I think were quite influential at the beginning of the field of Bayesian deep learning are Graves 2011, where there is the first implementation of mini batch variational inference. And this was quite significant because now you can scale to virtually any number of data. You know, you mini batch your objective, your variational objective, you can go fast. And also in 2014, the first version of mini batch Markov chain Monte Carlo sampling using hybrid Monte Carlo, which is also what we use here in this work. And importantly, I think, you know, 2016 has been really like a big change, you know, in terms of implementation of these models, because TensorFlow was released. And this is really like was a spectacular advancement for us, because I don't know, I mean, I see a lot of young faces here. When I was younger, I had to take derivatives by hand, of course, and implement gradients myself, debug this implementation, and make sure that everything would work. Now, all this has been sort of offloaded to these environments to develop, like TensorFlow, PyTorch. It's relatively easy now to just come up with an objective function, and then, you know, automatic differentiation works for you and gives you derivatives, and you can just do the optimization with this amazing stochastic optimizers that are implemented. And so I think this was really like a turning point for a lot of machine learning in general, but also I think for Bayesian deep learning, because then it was sort of easy to implement a lot of different crazy variational approximations and so on for these models. Around the same time, dropout has been viewed as variational inference. So for those of you that don't know this work by Yaringal and Zubin-Garamani, so the idea is that, you know, you do dropout at training time, and then when you want to make a prediction, instead of fixing dropout mask to make a prediction, you just resample this dropout mask many times, and so you get a lot of like a family of predictions that you can use to quantify uncertainty. And also around the same time, I think it was NIPS 2016, there was the first workshop on Bayesian deep learning and NeurIPS. And it's quite interesting because if you had tried to do convolutional neural networks with like a Bayesian treatment of all the parameters, you know, convolutional filters, fully connected layers, and so on, before 2016, I don't think it would have been possible. At least I'm not aware of anything that was practical enough to be usable in 2016 to do like a fully like a Bayesian convolutional neural network. And, you know, with this dropout idea, this became quite easy because dropout we know how to do. It's pretty easy and it works pretty well. And then, you know, at test time, you get some sort of distribution over the prediction. So that's quite significant. And you know, when I do my literature reviews, I cannot find anything more practical that you could use before that time to do convolutional neural networks in a Bayesian way. And so the question is then, you know, the field of deep learning has developed so much, and why people don't really use Bayesian deep learning in lots of applications? So why is it not like mainstream? If we can do uncertainty quantification so well with these models? Well, maybe some people still think that, you know, if you're Bayesian, you go slow. And now I wouldn't say so, because these days, I mean, we use stochastic samplers. And so if you do stochastic optimization and you're not Bayesian, you still have to tune sort of these step sizes, and, you know, have some annealing schedule for the step sizes and stochastic optimization. So still, it's going to take some time. In stochastic optimization, you know, you have some, unless the objectives are strongly convex, where you have, you know, fast convergence, you know, it's pretty slow in general. So I wouldn't say that being Bayesian makes you slower, I would say. And cumbersome to tune and implement, also the same thing. You know, we're going to have step sizes to tune in optimization, in stochastic Markov chain Monte Carlo sampling. We also have the equivalent of that. So it's sort of the same kind of difficulty in tuning these algorithms. But the hard truth is that if you take variational inference and try on a convolutional neural network of a reasonable size, take a VGG16 or your favorite ResNet or whatever, try this approach and get the predictive performance of these and compare against like just simple optimization. You know, the performance you get is like significantly lower in terms of accuracy, predictive accuracy. It's, you know, you get some quantification uncertainty, but the quality, I mean, the predictions are not that great, okay? So then you wonder, why should I be Bayesian, right? So if I don't get very good performance, maybe I should do something else. And we argue, and I think that this is really what has been our quest in the last couple of years, is really try to get to the bottom of the problem, which is the priors. So if you have a very large model, you're going to have millions of parameters. You're going to have to specify a lot of priors. And actually, you know, if you don't know, usually what do you say? Well, I don't know, so I'm going to put a Gaussian, you know, 0 mean, standard deviation 1, and I'm happy with that. And if you do that, that's a catastrophic thing to do in general, because you are heavily pushing your model, your prior in a part of the space which is not very good in terms of what the likelihood tells you, right? So you're putting the prior in a place which is not very compatible with the likelihood, let's say. And so this is really going to bias, if you want, in small data regimes, it's going to bias your results towards something which is nonsensical, as we're going to discuss in a minute. And this is a difficult problem. Now we have to specify priors for millions of parameters. And so how can we do it? And the problem is really that if we stick to this reasoning at the parameter level, it's really difficult to understand what is the effect of choosing one prior in the effect of, you know, what kind of functions we're representing, right? So our idea is really to say, so, you know, most people would resort to something like Xavier type prior variances, 1 over number of incoming neurons to any layer and so on, or 0, 1. And so we could choose this for convenience, but really this is going to have catastrophic effects, as we're going to see in a second. So instead of reasoning about parameters, why don't we reason about functions? So what kind of functions can we represent with these models? And so what we're going to talk about in this talk here is talking about functional priors. And what do we mean by this is the following. So we have parameters, we assume a prior for the parameters, P of W, and we can sample from this, right? Whenever we sample, we can forward simulate the input of the network, and we're going to get some outputs, okay? So the distribution of these outputs, P of F, is what we consider a functional prior, okay? So in our case, P of F given W is deterministic, because if the network is deterministic in the sense that, you know, give me W, I know how to forward propagate my computations from the input to the output, all right? So it's some sort of delta there, this P of F given W, but it captures the complexity of this network, right? And so now, what kind of P of F do we get? And so this is like a small animation that I really like, because it shows that we have a neural network here of how many layers? Like 3 layers, I think, or I don't remember now. I think it's 3 layers neural network. And you see that by just playing around with the standard deviation of the prior for the weights and the biases, you see that you get a very uncontrolled effect on the functions that you can represent. And there are configurations where these priors are completely degenerate. You know, the functions that we can generate from these models are super flat, in this case, for example, or extremely peaked around, you know, the origin, and then flat otherwise. And maybe, you know, this might be priors you like, but in general, maybe we don't like these priors to be super flat. Maybe there are some characteristics we would like to impose on these functions. And how can we do it? This sort of pathology of prior functions has been discussed a lot in 2014. For example, there's a nice, beautiful paper by David Duvenot, where there are beautiful illustration of this. I think it's called Pathologies of Very Deep Gaussian Processes, where you immediately see that by composing these functions, effectively these layers, the effect of saturation plays a big role here, and you can get some functions which are some prior configurations which are not very good. All right, so that's pretty much all I wanted to say in this introductory part. Do you guys have any questions, or all good for now? Okay, then Ba-Hien, you take over from here. Thank you.
Thanks, Maurizio, for introduction. Hello, everyone. My name is Ba-Hien. I'm a second-year PhD student. As Maurizio mentioned, reasoning the knowledge work in the parameter space is very difficult. So in the first part of my presentation, I will introduce the novel approach to impose priors directly in the function space instead of the parameter space. So in this work, we aim to specify the prior for Bayesian knowledge work in function space by means of Gaussian processes. Gaussian processes are a popular Bayesian tool for choosing sensible priors of a function. Gaussian processes are fully characterized by a mean and covariance function. By definition, a function is distributed to a Gaussian process if and only if the evaluation of the function at any finite set of inputs is a jointly Gaussian, and the mean and the covariance of the Gaussian can be obtained by applying the mean and covariance function on the input data. As Maurizio introduced, there is actually a connection between Bayesian knowledge work and Gaussian processes. News show that one hidden layer of Bayesian knowledge work will converge to a Gaussian process in the limits of infinite number of hidden units. Because Gaussian processes are fully characterized by a mean and covariance function, different choices of the covariance function result in different prior in function space. A popular choice covariance function is the radial basis function, which is characterized by two hyperparameters, which are the length scale and the variance. As can be seen that we can control the smoothness and the marginal variance of the prior function of Gaussian processes by modifying the length scale and the variance respectively. The main research question in this work is how to impose functional priors for Bayesian knowledge work so that we can exhibit interpretable properties similar to Gaussian processes. In particular, we would like to match the prior of Bayesian knowledge work to a Gaussian process prior in function space. However, this is a very difficult task. First of all, we are trying to compare to stochastic processes. This means that we are comparing to infinite dimensional distributions. Secondly, we don't know the closed form of the density of the Bayesian knowledge work prior. Usually, we can only sample from the Bayesian knowledge work prior. This makes it very difficult to use some popular metrics to measure the similarity between two distributions like KL divergence. For example, as we can see that the KL divergence between the Bayesian knowledge work prior and Gaussian process prior consists of two terms. The first term is the cross entropy, which can be estimated analytically because we can evaluate the Laplaceity of Gaussian process prior. The second term is the entropy of the Bayesian knowledge work prior, which is intractable because we don't know the density of the Bayesian knowledge work prior. So in order to solve this problem, we consider the dual form of one Wasserstein distance to measure the similarity between two distributions. Wasserstein distance turns the problem of estimating the distance between two distributions into an optimization problem. In particular, it is effectively a functional maximization of a phi on the difference between two expectations of phi under two probability measures, which are p and tau. And here we can train the Lipschitz function so that is one Lipschitz. An advantage of this form is that we don't need to know the closed form of two distribution, tau, b and tau, because we can estimate the expectation by samples. In addition, we can parameterize the Lipschitz function by a knowledge work so that we can optimize the Lipschitz function with gradient descent methods and backpropagation. The figures on the slide show a scheme of our method, and our method aims to minimize the one-Watson distance between Bayesian network prior, denoted by a green block, to a target GP prior, denoted by blue block. And we would like to match Bayesian network prior to the target GP prior as a finite number of measurement points sampled from a distribution Q. And here we parameterize the Lipschitz function by a neural network denoted by a red block. And we would like to optimize the prior parameters. For example, they are the variance of the Gaussian priors for each layer of neural network. And we alternate maximizing the objective function with respect to the Lipschitz function. And then we minimize the objective function with respect to the prior hyperparameters. The inner optimization aims to estimate the one-Watson distance between the sample from the function sample from the Bayesian network prior and Gaussian process prior. And the inner the optimization aims to optimize the prior hyperparameters so that the one-Watson distance between Bayesian network prior and the target GP prior is minimized. And at the end of the optimization, we obtain a GB induced prior for Bayesian neural network.
One question. So what do you do with the target Gaussian process prior has a certain length scale kernel, right?
Yeah.
And is that fixed, or how do you estimate the kernel parameters of that?
Yes, actually we can optimize or we can use a fixed kernel, and I have a discussion about that in the following slides.
Okay.
Yeah. So an advantage of our objective function is that it's a fully sample based. As a result, we don't need to know the closed form of the marginal density of the Bayesian network prior. In addition, instead of using Gaussian processes, we can consider any stochastic process as a target prior of a function. There is only one requirement, that's if we can sample that from that stochastic process. In addition, the objective function can be optimized with gradient descent algorithms with backpropagation. Because Bayesian networks and Gaussian process priors are stochastic processes which are indeed infinite dimensional distributions. In order to have practical and well-defined optimization strategy, we match Bayesian network prior to the target GP prior at a finite measurement point sample from a distribution. For low dimensional problems, we can simply use a regular grid, or we can sample uniformly measurement points from the input domain. For high-dimensional problems, we can sample from the training data. We may also apply some augmentation on the training data. Lastly, in some application, we can know the input region of the test data points. In these cases, we can set the measurement distribution to include those regions. Our framework is flexible and supports many types of prior parameterization. There are only two requirements for prior parameterization. Firstly, we can draw sample from the prior. This is required by our algorithm. Secondly, we can compute the log density of the prior. This is required by many inference methods like rational inference or stochastic gradient, Hamiltonian Monte Carlo methods, which we mainly use in this work. And in this work, we consider three different parameterization. Firstly, we consider the typical Gaussian prior. In particular, we consider layer-wise factorization, Gaussian distribution for the weights and biases. The parameters to optimize are the variance for each layer. Although this is a very simple parameterization, and it is sufficient to capture the target GP prior in many cases. A more flexible family of priors is a hierarchical prior, where we further place a hyperprior on the variance of the Gaussian prior. And here we use an inverse gamma hyperprior, and we optimize the shape and the rate parameters of the inverse gamma hyperprior. And some recent work show that heavy tail priors are better than Gaussian prior for deep neural network. And actually the hierarchical prior is considered a heavy tail prior. Lastly, we consider normalizing flow as a prior for Bayesian networks. And the main idea of normalizing flow is that we transform a simple distribution like standard Gaussian distribution into a more complex distribution by using a sequence of vertical transformations.
Sorry, could you go back one slide?
Yeah.
So the normalizing flow prior, that's the only one that's really capturing correlations between the weights, right? The hierarchical prior is just like more robust, right? But it's still factorized over the weights, right? Okay.
Yeah.
Okay. Yeah. Thanks.
The animation on the slide illustrates the optimization process to mask the Ba-Hien prior to a target GP prior on one-dimensional dataset. And here we use the normalizing flow prior. And thanks to the flexibility of the normalizing flow, we can see that the Ba-Hien prior can mask closely to the target GP prior. And the resulting prior can capture the characteristics of the target GP prior, such as the length scale and the variance. The figures on the slide show the result with different families of the prior. And here we use a 3 hidden layer neural network with an ice activation function. The green plots illustrate the functions sampled from the fixed prior, such as the standard Gaussian prior. And we can see the pathology of the standard Gaussian prior as the induced function are flat. The orange plots illustrate the function sampled from the optimized prior named GB induced prior. And here the target GB prior is illustrated by the blue plot. And the last rows illustrate the convergence of one-Wasserstein distance optimization. We see that the GB induced prior can capture the characteristics of the target GB prior. And as mentioned in the previous slides, the normalizing flow prior can mask slowly to the target GP prior as evidenced by very low one-Wasserstein distance. The plots on the slide show the both series collected by running HGLMC with the corresponding priors. And as can be seen that as we can see that the fixed prior tend to provide a flat solution. And besides, the predictive procedures provide overconfident in the reason without the training data. Meanwhile, the procedure corresponding to our GB induced prior provide better uncertainty quantification. And this demonstrates that choosing prior is very important for Bayesian network. Do you have any questions so far? Yeah.
Did you empirically investigate the distribution of the variances for the Gaussian prior, for example? I mean, it would be super interesting to see if the variances are maybe smaller at early layers and wider at large layers. Is that what you see?
Yes. Actually, we also investigate how the resulting variance for each layer. And it depends on the network architecture and the problem. For example, in this case, we observe that the prior variance should be large in the intermediate layers. It should be small in the input and output layer.
Oh,
yeah.
Because there's a lot of evidence that sort of being Bayesian in the last layer of the neural network works.
Yeah.
Right? But being Bayesian in earlier networks can be harmful.
Yes.
So I was expecting that the variance grows as you go closer to the output.
Yeah,
it's interesting to see that it's.
Yes, I think it makes sense because this result show that we should tune carefully the prior for the first and the last layer, and the variance of the intermediate layers large, that maybe we would like to impose more flexibility for the intermediate layers. And by using our method, we can see that our optimized prior can capture the properties of the target GP prior. The figure illustrates the predictive procedures from Bayesian network prior, from Bayesian network corresponding to the optimized Gaussian priors by using our approach. And here we consider the Gaussian process with an RBF kernel as the target prior. And we can see that by using our approach, we can effectively define the regularization trend of the prior in a sensible way. by modifying the parameters of the IBF kernel, like the length scale and the variance. And we can see that the decision boundaries are more complex for shorter length scale and larger variances. And the question now is how to choose a suitable target GP prior. The most common approach is to select the hyperparameters of the target GP prior by optimizing the marginal likelihood. However, this approach introduces additional complexity to solve GP, especially for the case of big data. In addition, the optimized GP may be useless. This is because the optimized GP may not be suitable for Bayesian network. And ideally, we should try and compare a set of possible combination of hyperparameters. However, this approach is impossible in practice because the cost is very huge. So in order to overcome this problem, we consider a hierarchical form of the target GP prior. In particular, we further place a log normal or hyperpriors on the variance and the length scales. Then the sample from the target prior can be obtained by using a gift sampling scheme. For example, firstly, we sample from the variance and the length scale from the log normal hyperprior, and then we sample function accordingly. By this way, we implicitly consider on cases of kernel parameters, and as a consequence, we define a more flexible distribution of the functions. And as can be seen that the predictive procedures of the Bayesian network corresponding to the hierarchical prior is very reasonable. And in this work, we employ the hierarchical GP prior in most experiments. The next experiment, we show the importance of choosing a good prior for modern convolutional like VGG or ResNet. In this experiment, we compare two deep ensemble with a practical methods for uncertainty quantification by combining multiple non-Bayesian network solutions. We also consider the fixed Gaussian, which is the standard Gaussian prior. With temperature scaling, this is also a practical method to handle model misspecification by scaling the true procedures. And the results from the table show the effectiveness of our functional prior as evidenced by consistent improvement in performance when using GP-induced Gaussian prior and GP-induced hierarchical prior compared to using fixed Gaussian prior and fixed hierarchical prior. And we can see that our GP-induced hierarchical prior offers the best performance in most cases. And we would like to emphasize that choosing a suitable prior for Bayesian convolutional is very important. And we show that if we choose a good prior, the performance of the true procedures may be better than performance of the non-Bayesian method or temporal procedure. Yeah.
So how would the adjusted Gaussian process model work? I mean, like you're trying to make Gaussian process look like a neural network. But what if you just use the Gaussian process model for regression and classification?
Yes, the problem is that because Gaussian process may not work very well on high-dimensional data like image. Meanwhile, network is can work very well on high-dimensional data like image. And the problem of Gaussian process is that is the difficulty of the choice of the kernel, so that we can work on very high-dimensional data.
Maybe if I can complement also, like there is actually a convolutional Gaussian process paper, where they actually try to compare, how much you lose by not having a structure given by convolutional filters in the problem. And so I think I don't remember the numbers exactly, but for MNIST, I'm pretty sure that you can just apply GP, one of the best GPs you can think of, you get 98-point-something% accuracy, whereas with a simple, like the simplest component, you can get more than 99. Some people would argue that maybe with a GP, you can get 99%, and there are some, papers out there that they say, but it's generally pretty hard because you're not imposing any structure in the problem. Whereas with convolutional neural network, you have that structure in the design. So for CFR10, I don't remember, but it might be that you get 60% accuracy with the plain GP. I think that there's a huge gap when compared to these kind of comments.
Yeah. Do you have any questions so far for my first part of presentation? If no, I can move to the second part of my presentation about how understanding of this work for unsupervised learning settings. So in particular, I'm going to present a novel method for model selection for Bayesian autoencoders to solve some unsupervised learning problems like representation learning and generative modeling. In this work, we consider autoencoder models, which are a kind of neural network used for unsupervised learning. An autoencoder consists of two neural networks, which are encoder and a decoder. The encoders transform high-dimensional inputs into low-dimensional latent codes, while the decoder is used to reconstruct the input data from the latent codes. And here we can consider Bayesian autoencoder as a Bayesian neural network for supervised learning, where the target Y is exactly the input X as we aim to reconstruct the input data. From this perspective, by using the Bayes rule, we can compute the posterior distribution after observing the data. We see proportional to the prior and multiply the likelihood. Because the target Y is exactly the input X, so in the following slides, we replace Y by X for simplicity. The Bayesian treatment of autoencoder provides some important benefits such as quantification uncertainty, which is a primary requirement for high-risk application, such as self-driving cars or healthcare application. In addition, thanks to the Bayesian treatment, thanks to the Bayesian scheme, we can incorporate a prior belief into the model in a principal way. This is very helpful in the case where the training data is very small.
I'm sorry. I guess I missed the model. So how's the model defined? I don't understand the figure.
What?
Yeah, any of those. Can you explain this again? So how do you define a Bayesian autoencoder?
Actually, we can consider the Bayesian autoencoder as a Bayesian neural network for supervised learning. And here, the target Y is exactly the input X as we aim to reconstruct the input data.
Okay, I see. So you concatenate X and Y and
yeah.
you do an autoencoder.
Yeah, and we can SE actually a Bayesian neural network.
No, I see what you mean. No, we have no labels.
Yeah.
Okay. We just go back to the setting where Y, we consider Y as the labels of our problem. But now we say Y is equal to X, just because we want to reconstruct. So we have some inputs and we want our labels to be exactly X, right?
Oh, I see. So are you just saying that, an autoencoder can be made Bayesian by
just putting a distribution?
Yeah.
Okay.
Yes. Right. It's different from rational autoencoder. In rational autoencoder, we impose the prior on the latent space, and here we impose prior on the parameters of the neural network.
So, but it's not a generative model.
No. Yes, in nature, it's a generative model, and we have on the process to make it a generative model.
What you've written here doesn't seem like a generative
model.
Yeah. So far, no. Okay.
Yeah.
Thank you.
So the second benefit of our Bayesian autoencoder is that we can incorporate prior knowledge into the model in principal way, and it may be helpful for small data problem. However, Bayesian autoencoder is not a popular choice for representation learning or generative modeling because of several reasons. The first one is that the postures of the Bayesian autoencoder is intractable, unlike rational autoencoder, which rely on rational inference. This may lead to poor approximation. We handle this problem by Bayesian for Bayesian autoencoder by sampling from the true postures by using a stochastic gradient Hamiltonian Monte Carlo method, which is well known for efficiently exploring the posterior space. The second problem is that the Bayesian autoencoder in nature is not a generative model. To address this problem, we perform density estimation on the learned latent space with a linear process mixture model. The last problem, and also the main focus of this work, is to choose a sensible prior. Once again, choosing a prior is the most important and often the most difficult step in Bayesian modeling. Specify in the prior for Bayesian autoencoder is also not trivial. Let's assume a prior distribution on the parameters with size is the prior hyperparameters to be selected. For example, in the case of Gaussian distribution, size consists of the mean and variance. Because an autoencoder is characterized by a huge number of parameters and non-linearities, this prior on the parameters induce a non-trivial effect on the function space. For example, the standard Gaussian distribution is the most popular prior for Bayesian neural network. However, as can be seen that from the figures that the sample realization obtained by sampling parameters from the standard Gaussian prior indicates that this choice provide a poor inductive bias in the function space. So in this work, we propose a novel method for choosing a meaningful prior for Bayesian autoencoder based on the empirical based approach. In the Bayesian framework, a principal approach to select the prior is to rely on the marginal likelihood. In particular, we would like to maximize the marginal likelihood with respect to the prior hyperparameters. In our case, the marginal likelihood can be obtained by marginalizing out the output X hash and the model parameters W. However, in the case of Bayesian autoencoder, estimating the marginal likelihood or even its lower bounds is not trivial. And there is equivalence between maximum likelihood estimation and KL divergence minimization. And maximizing the marginal likelihood over the data generating distribution, which is denoted by PS, equivalence to minimizing the KL divergence between the marginal likelihood and the data generating distribution.
There's a log, extra log there.
Yeah.
So the marginal likelihood is just the integral of pi x times p of cx.
Yeah. However, matching these two distributions with KL divergence is not trivial. So to overcome this problem, we propose to replace KL divergence with the distribution noise lies Wasserstein distance because it can be estimated by using only sample from distributions. Moreover, this distance can express two major constraints that are the scalability tends to using random projection for estimating the Wasserstein distance. In addition, this distance can work very well on high-dimensional data like image. So our objective is fully sample-based and can be optimized with a gradient descent algorithm with backpropagation. And as a consequence, we don't need to know the cloud form of both the marginal distribution and the data generating distribution. The only requirement is that we can draw sample from these two distributions. In order to sample from the marginal distribution, we firstly sample parameters from the prior over parameters, and then we compute the output X hash accordingly, and then we sample from the likelihood BX given X hash.
Could you once more explain how you construct a generative model from this? So the prior is now another generative model that produces data X, and that gets then fed into the autoencoder as a likelihood?
No. I will discuss how I can max Bayesian autoencoder to a generative model later.
Right.
Yeah.
Okay.
Yeah.
Okay.
I will discuss about that. So in the first experiment, we use a small set of the MNIST dataset for optimizing the prior, and then use another set of MNIST data for inference. The first figures on the slide show the conversions of the Wasserstein distance during prior optimization. And the right figure showed a comparison between our approach and some competing methods like vanilla fractional autoencoder, beta fractional autoencoder, and Bayesian autoencoder with standard Gaussian prior. And for a fair comparison, the competing methods use the whole training data which I denote by a star symbol for inference. It can be seen from the results that our approach, which is denoted by yellow color, outperforms other methods across different training size despite using less data for inference. The left figures show that our optimized prior induce a much better inductive bias compared to the standard Gaussian prior. It can be seen that by encoding better belief into the prior, the sample from the optimized prior can capture the main characteristics of the data, even when the models is given by out of the distribution data. The right figures show a low-dimensional projection of parameters sampled from prior and posteriors, as we can see that the hypothesis space induced by the standard Gaussian prior, which is denoted by brown circles, is very huge compared to where the true solution should lie, which is denoted by red triangle. Being white tends to a good inductive bias the hypothesis space of the optimized prior, which is denoted by yellow circles, is reduced to regions close to the true posteriors. Therefore, we may need a small dataset for inference to obtain a sensible results. For example, in this experiment, we only use 500 training samples to optimize prior and 1,000 training data points for inference. So as previously mentioned, different from Bayesian autoencoders and other models, Bayesian autoencoder is not a generative model. To generate a new sample with Bayesian autoencoder, we employ density estimation over the learned latent space. In particular, after training the model, we firstly generate latent cost with respect to the training data. And then we use a dirichlet process mixture model, which is a flexible non-parametric model to estimate the density of the latent space according to the latent cost. A new sample can be obtained by firstly sampling a latent cost from the dirichlet process mixture and then making a prediction using the posteriors of the decoder accordingly. Is clear so far?
Yeah. So are you saying you take an input, or you look at all the encoded data points, right?
Yeah.
Marginal posterior, so to speak, and then you fit a density model.
Yeah.
And then you sample from the density model, and
yeah.
So that's this them prior idea in the classical BAE setup, I think, right?
Somehow similar to them prior. Yeah.
Mm-hmm.
In this slide, we show experimental result on more challenging dataset with CelebA. In this experiment, we consider a wide range of baselines such as rational autoencoder with more complex encoders by using C-vector normalizing flows, or more complex generators by using two-stage rational autoencoder, or more complex priors such as the VAM prior. In addition, we also compare two different types of GAN, such as the vanilla GAN and the more recent differentiable augmentation GAN, which is designed for small data problem. Here we use the same network architecture for autoencoder models and vanilla GAN. The differentiable augmentation GAN is employed with a more complex network architecture, and we compare the methods in terms of reconstruction, quality, and generative modeling by using the test log likelihood and FID score, respectively. It can be seen that our approach is denoted by yellow colors outperform on fractional autoencoder model and vanilla GAN. The differentiable GAN use better FID score. This is not surprising because this model use a much more complex network architecture and a powerful differentiable data augmentation scheme. So we have shown that choosing sensible priors for deep Bayesian models is very important and difficult because Bayesian deep neural network are characterized by a huge number of parameters and non-linearities. So in order to tackle problem, in this work we propose a novel objective function based on the Wasserstein to impose a sensible prior directly in the function space. And we conducted an extensive experiments, and we showed the benefits of our approach. Besides, by using our priors with scalable MCMC sampling, we show that a fully Bayesian treatment of deep learning models can provide a large performance gain. We are currently trying to apply our work on some particular problems like data augmentation and fairness. In terms of application to domains beyond machine learning, we think that the next step should be to scale fully Bayesian modeling to massive scale data and models. These are important for application in decision making involving real data in various applications such as environmental science or life science. Another important aspect is not only to able to use machine learning for sustainability, but also reduce the carbon footprint of current machine learning approach by using light-based computation or fast approximation. I was list to some publication at the GMOA and NORIS, and you can find more interesting results and detailed analysis by checking our paper. Thank you very much for your listening. Do you have? I would be happy to answer if you have any question.
Yeah, any questions? So let me maybe start with one. So what's actually the main advantage of Bayesian autoencoders? So what are these models used for? I have actually one application in mind, but I'm just curious what they're usually good for, right? I mean, what's the goal?
Let's come back to the motivation of Bayesian autoencoders. And in my mind, there are two clear benefits of using our Bayesian autoencoders. The first one is that we can quantify of uncertainty. Maybe it's useful for some safety critical application, such as the healthcare or self-driving cars. And another benefit is that we can specify a prior belief or prior domain knowledge, which it may be helpful in some particular application where the training data is very small.
But your question is more about autoencoders, like plain autoencoders.
No, Bayesian autoencoders.
I think, anytime you have a variation autoencoder that you want to use, you could say, well, instead of using that, why not just a plain autoencoder? I think this idea came from a project I had with some students, where I was curious about this randomness that you impose in the variation formulation in the latent space, or the one that is induced by having a distribution over the weight. And so my question was, from the modeling perspective and representation of representation learning, is there really a difference? And it turns out that either you put that randomness directly in the latent space, or you put it in the weight. Somehow you get similar results. And so I thought, okay, now that we have a good way to expect priors, maybe that we should consider these and get away from move away from variational approximation. It seems like there are some benefits in doing that. So yeah. But
okay, so it's really just like an alternative generative model or whatever.
And also, yes, projection, non-linear projection with uncertainty.
Actually, when we work with a rational autoencoder, we have to face a lot of problems, such as how to choose the approximation procedures, and another one is also how to choose a good prior.
More questions?
I have a question. If I may be discussed, but I was wondering if there are these dynamic autoencoders, and I thought the Bayesian method actually putting prior, which is something like GP, would make more sense there to allow for that projection to change. Is it something that I've been discussing with my students and haven't done it yet? I don't know if you know the literature, if other people have.
There is definitely like a GP, a variation autoencoder where there is a GP on the latents.
Yeah, yes. There is actually some work on using the Gaussian project as prior over the latent space of variation autoencoder.
I'm sure I can retrieve this.
Yeah, we should publish 2 papers on this.
Yes. And it was from your group.
Yeah.
There you go. That's what I read. There you go. That's what I read about it. Because now I was mixing things up. I thought maybe it was from the other group. But,
no, but it was sort of a collaboration with some people at PH. But yeah, I can point you to some papers. Cool. You have some interesting story that might be interesting, some use case for Bayesian autoencoders also related to data compression, but maybe it's easier to talk offline.
Yeah.
So they have a big research.
Yeah, we do a lot on data compression and these kinds of generative models. Yeah. Cool. All right. There are no more questions, and thank you very much. Really interesting. Cool. Okay.
We're within the hour. It's very
great timing. I had actually one master's project on